All right. So this is going to be another somewhat mathy lecture, but we're now ready to upgrade ourselves to multidimensional Coulomb forces. So just to recap where we are, before we had this equation on the screen. I'm going to move my mic actually real quick, so apologies for whatever you're about to hear. There we go. Yes, much better. Before we were talking about one-dimensional Coulomb forces, and we talked about how the magnitude of the Coulomb force is given by this expression. It involves a constant, then the absolute value of the charges, and then the square of the distance between them. And with the idea that this is giving us, now if we think of this in terms of vectors, this gives the magnitude of the force. How much force is there in newtons? And then the direction is based on the sign of Q1 and Q2. So say sign of Q1 and Q2, where if we draw a picture, we're dealing this in one dimensions, so put Q1 here, Q2 here. They're connected by a dotted line. That the force acting on Q2 from Q1 is either going to be pointing away or towards. Similarly, on Q1 from Q2, either away or towards. The direction is along the line connecting the two. And the direction of the arrow is somewhere along the line connecting the two, pointing either away or towards the other charge, depending on if it's attractive or repulsive. So, what are the goods of kind of writing Coulomb's force down this way? I would say the good is that it keeps you thinking about what you're doing. What I mean by that is that you can't just blindly start plugging things into an equation and get an answer, but you actually have to think about what's going on. You have to imagine, you have to draw the charges, you have to draw the line connecting the two, and then you know the force is either going to be pointing towards or away along that line, and then you have to think about the charges and whether it's attracting or not. So, I'm of course on board because it keeps you thinking. The bad is that this approach is very hard to scale. It's not too bad when you have two forces, but you can't really do this if I were to, on an exam, give you 100 forces or 100 charges. Now, of course, I'm not going to give you 100 charges on an exam, but while I might not give you 100 charges, I might give you a continuum of charge. For example, I could say that there is a thin wire that is located, say, here, and there's charges all along the wire. It's a piece of copper, and I put some positive charge on the copper wire. And then if I have some Q that's located some location away from the wire, I might want to know what the force is on that charge from the wire. But in that case, then I can imagine that essentially then I have to do a Coulomb's law of force problem, but there's literally infinite charges, because I can imagine taking this wire and breaking it up into a bunch of tiny little pieces, each of them located at a slightly different location, and maybe each of them have some charge, a little dq. And each of those little dq's are exerting some force. So there's a bunch of, suppose that everything is positive forces here. There's a bunch of positive forces. There's all these little force vectors that are pointing, and then we have to add them all up. Can't really do that by hand the way we've been doing it for 1D. So we need a way to generalize. We need a generalization of how I evaluate this force. And for this lecture, we'll stick with it being between 2-point charges. And we'll worry about the calculus versions maybe next lecture, or definitely next week at some point, where I am now kind of actually looking for some sort of formula where I can algorithmically do some steps and know that I'm going to get the right answer as long as I'm careful and as long as I do the steps correctly. This, of course, then is how you might think about this if this were a computational problem. If you're doing this on a computer, you want some algorithm, some process of doing this so that no matter what is thrown at you on the computer, this would compute the right answer. And use gravity as an example, right? If I were to do a gravitational simulation of a solar system, right? It should not be a code that I write super explicitly to only do the sun and the earth. Because what if I want to throw in the moon? What if I want to throw in Mars and its moons? The 93 moons Jupiter has, at least, as of last year. I need something that can generically and algorithmically evaluate to the right answer. And this is a great example of kind of just the inductive process of science. We're going to take examples where we're going to know the answer. We're going to know how to evaluate this, explicitly, because they're essentially going to be 1D problems. And we're going to try to generalize to something that could work no matter what we throw it as the problem. So let's work through it with this example. And in doing so, you'll see that essentially I will be doing this and be able to write it down in 2D. And if you can do it in 2D, you can do it in 3D, you can do it in 10D. So let's have two charges I've drawn on a Cartesian axis. I'm going to place one of them at the origin and the other one along the x-axis. And they're separated by distance r. So essentially this is a 1D problem. One where we know what the answer should be if I tell you the sign of the charges. And so what we're going to be asking is, what is the force on Q1 from Q2? Then I might want to know what is the force, because again, I should be able to write something down that's super generic, where if I want to do the force on Q2 from Q1, I should be able to do that for me as well. And if I put them on the y-axis instead, I should still be able to get the right answer. And then if I put them, say, at a diagonal, where I need both the x and the y-axis, it should still allow me to get the right answer. So let's do this as if this were in a science experiment, where we're going to make some observations that we're going to use to generalize. So, and we want to be able to do this generically, so of course this is going to end up using the language of vectors. So, what do we notice? Well, let's use some test cases. Let's dream up some test cases. So let's imagine that both Q1 and Q2 are positive. Then what would be the force on Q1 from Q2? I'm going to focus on this for right now. On Q1 from Q2. So if Q1 and Q2 are positive, what direction do you expect the force to point? So if I have, that's Q1, then I expect them to repel one another. I expect the force to be point in this direction. So I'm going to write force Q1/Q2. And again, that's going to mean on Q1 from Q2. Okay, if Q1 and Q2 are negative, both negative, then I expect the same answer. I expect them to repel one another. I expect the force to also point to the left. if, and then what's left, if Q1 and Q2 have opposite signs. One's positive, one's negative. No, I don't necessarily have to say which is which. I just need one of them to be positive, one of them to be negative. Then I know it's going to be attractive. And the force vector is going to point in the opposite direction. So it seems in this case, some data I have is that when they have the same sign, whether it's positive or negative, I could lump these together and just say, Q1 and Q2 have the same sign. They're both positive, they're both negative. The force points in one particular direction. When they have opposite signs, the vector should flip. So that's something that whatever we come up with should be, obey. Because essentially, to think about what I want to be able to do here, I want to be able to write something generic that also doesn't necessarily have these absolute values, for example. I want to get rid of those absolute values. So that if they have the same sign, Q1 times Q2, that's going to be a positive number. Might as well just write that down, right, to remind ourselves. If both are positive, then Q1 times Q2 is going to be greater than 0. 3 times 2, 6 times 8, whatever. If they're both negative, then again, Q1, Q2 is going to be greater than 0 because you have two negatives. And then if they have opposite sign, then Q1, Q2 is going to be less than 0. So that seems useful because, again, it seems like when they both have the same sign, I want the vector to point one way. And when they have the opposite sign, it points the other way. So Q1 times Q2 will provide that negative to flip the vector around if they have opposite signs. So if I can come up with a formula that works for when they both have the same sign and points in the right direction, then when Q1 and Q2 have opposite signs, that'll flip the vector around. All right. Let's see. Let's go to another page. Oh, whoops, those are my notes if I have to copy anything. So let me copy and paste the problem. Okay. So those are some observations about sign. And now again, let's think, if they have the same sign, they're both positive, they're both negative, then let me make another copy of this actually. But I'm going to get rid of this. This essentially is 1D. If they have the same sign, then I know the force vector is going to point in this direction. Now, the force vector we know from when we talked about at the beginning of this lecture must be somewhere located on the line that connects the two charges. So I know the force vector is located, it was supposed to be a dotted line, somewhere along this line. And again, of course, we've drawn it that it's pointing to the left in this case. So since I want to ultimately think about this in terms of vectors, is there a vector that points along that red dotted line that somehow is connected to the charges? Well, the vector that points to Q1 from Q2. Let's look at that. So consider R, which is going to be a vector that points to Q1 from Q2, which we talked about last lecture is then going to be the difference of the two position vectors. That's going to be the position vector for Q1 minus the position vector for Q2. And again, remember that this is, in this case, where it's to this from this, like a letter. So if I were to draw it up here, maybe I should have used a different color. Let's make it this. So points to Q1 from Q2, that looks like that's this vector here. It indeed is pointing along the same line, as it is parallel to that dotted red line I've drawn. So this seems like it might be a vector that it will at least get me the right geometric orientation for things. And then I can think about whether or not, throwing in a negative sign is going to get me the correct force. So let's think about it a little bit here. So what are these position vectors for this particular problem? For this particular problem, R1 is just 0 because I've conveniently placed it at the origin. And R2 looks like it's a location R in the x direction. I'll just write this as R x hat. Its coordinates, if you want to think of the coordinate for R2 in 2D would be R, 0. It's all along the x-axis. So in this case, it looks like R is, which again is R1 minus R2. Looks like it's 0, x. I guess I should state what the 0 is, right? I could make explicit the 0 vector, which of course is 0 x hat plus 0 y hat. But again, since this is essentially just a 1D problem, I'll just focus on the x hat. So it looks like it's 0 x hat minus, and then it was r x hat. So this vector looks like it's negative r times x hat. Does that make sense? Indeed. It points in the x direction, but it points to the left. So points to the left, in the x hat direction. Again, left because of that negative. So again, as I've drawn up above. Now, it seems like, again, what observations do we have? If Q1, Q2, I'll just say if the product is greater than 0, which is positive, which again means they're both positive or they're both negative. If Q1 and Q2 have the same sign, then it seems like F, Q1, Q2, and this R vector I just dreamt up are parallel. And then if Q1, Q2 is less than 0, which means they have the opposite sign, then it looks like F, Q1, Q2, on Q1 from Q2, and R are going to be anti-parallel. Because if the charges have different signs, that's going to change the direction of the force vector. It's going to point to the right. But this position vector R is not going to change, of course, because I haven't done anything with the positions. So all this is coming together because it seems like this R vector is going to be what's useful. Because it seems like when they're parallel when you have the same sign, and then when they have the opposite sign, which introduces a negative, seems like that might be what allows us then to write something down where then R and F are anti-parallel. So let's use this R as the direction. So we're going to use R equals R1 minus R2, in our equation for the force on Q1 from Q2. And what I like here is the symmetry that you have Q1 first, Q2 second, and then you have the position of Q1 first, the position of Q2 second. So the formula I'm coming up with is going to have a nice symmetry to it, which makes it easier to remember. So given this position vector, which we said is negative R x hat, And again, if I want to be explicit, right there's a plus 0 y hat. Or if I want to write it with brackets, negative r comma 0. Then the magnitude of this vector, what does the magnitude represent? That represents the distance between the two charges. Not sure what happened with that word. That seems like it should be useful because that is in Coulomb's law, the 1 over r squared. That r squared is the distance squared between the two charges. All right, well, as a vector, I know how to compute the magnitude. It's the square root of the dot product. So it's a square root of, looks like it's negative r squared plus 0 squared, or just r. Not too surprising, given the setup of the problem. And so therefore, if I want to focus on the direction of r, well, that of course is just r hat, the unit vector. So that is 1 over magnitude times the original vector. So that is 1 over r times the original vector, which we said was negative r comma 0. So it looks like then that is negative 1 comma 0, which of course is just negative x hat. And again, is that too surprising? Hopefully not, because the arrow, let's go back up, show this arrow. This arrow for the position is pointing to the left along the x hat direction. So it makes sense that the unit vector version should just be x hat in the left, pointing to the left. So in this case, this is just a unit vector pointing left. Which again, if the charges have the same sign, is the same direction the force should point. And if they have the opposite sign, it's the opposite direction the force should point. Seems like now we have everything we need to put together. Because it seems like then I can say the force on Q1 from Q2 is going to be equal to K Q1 Q2, no absolute value, divided by the distance between them, which is the magnitude of that r vector squared, multiplied by r hat. This magnitude, which might have a negative sign in it, which is okay. Though magnitudes are technically always positive, but that negative sign then just gets lumped into the direction. I won't worry too much about that. That seems like the magnitude still looks like k q1 q2 over r squared. Good. That matches our 1D version from before. And then this is giving us the direction, which will then satisfy that if Q1, Q2 is greater than 0, that implies that F is parallel to r hat. Good. Not write the subscripts. And then if one of them has the opposite sign, then there is a negative that's going to be located, there's going to be a negative overall over here, which then that negative you could lump in with the direction vector. And so then F is going to be anti-parallel to r hat. I believe this is the symbol for anti-parallel. Well, I'll just write out. Anti-parallel, parallel. Now, we have this example problem. We better make sure it makes sense before I start highlighting things. So, let's again go back to our original problem that we used to essentially motivate this definition. Let me copy it, throw it down here. Let's see if I can go through the steps and get the right answer, which I know, if they have the same sign, should point left. If they have the opposite sign, should point right. Let's give the charges. a sign. Let's say Q1 equals Q2 equals plus E. They both have the same sign. We expect our answer at the end of the day better point to the left for the force on Q1 from Q2. So I know K, I know Q1, I know Q2. Now I need to do all this R business. So the R vector, which we defined to be R1 minus R2, we again said that was 0 minus R in the x direction, or negative R x hat, plus 0 y hat, I guess technically. The magnitude of this thing we saw above was just R. And the unit vector we saw was just negative x hat. So then, let's put it all together. F on Q1 from Q2 is K plus E all over R squared, don't forget the square, multiplied by R hat, which we said was negative x hat. So that looks like this is K E squared over R squared, is a negative out front, times x hat. This is along the x direction. And then because of this negative sign, it points to the left. Seems like all is well, and this does actually work for our form, as a sort of general formula. Now that's one specific example, of course. We should be careful and make sure that we do a couple more examples before we generalize this thing, though this will be correct. So let's do some more examples. So let me write it down. The force on Q1 from Q2, we said is equal to K, Q1, Q2 over the magnitude of this vector squared, because that's the distance between them, multiplied by R hat, where this vector R is the position of Q1 minus the position of Q2. Points to Q1 from Q2. And this is kind of what we're putting up against some tests. Well, let's try a problem that's essentially still 1D. Really, for two charges, it's always 1D, because I can always rotate my coordinate axes to have them live along the x or the y direction. But let me put Q1 here and Q2 here. And so in this case, the line connecting them is not exactly the x or the y hat directions, or the y hat axes, but it's offset, such that the position vectors, which again, position vectors, we do draw from the origin as vectors. That's R1, and then the position vector R2 is this. And again, let's have them both be negative this time. So we'll have this be negative E and negative E. Or I can have one be negative 2E, because why not? Negative 2E. And then the question is, what is the force on Q1 from Q2? Now again, I can think and know that since they have the same charge, this force vector should again point to the left, because Q1 should be repelled and be pushed away from Q2. Let's see if our generic formula works. Well, I know K, I know Q1, I know Q2. So then it looks like R, which is going to be, by what I wrote above, R1 minus R2. And let's actually give some numbers. Let's say that R1, in this case, is, looks like it goes back a little bit. So we'll say it goes back -1 and then up 2, right, in meters. And then R2, looks like it goes, say, over 2 and up 2 in meters. So then they are located along the same y value, which makes sense the way I drew it. So in this case then, looks like I have kind of -1, 2, minus 2, 2. I'll be a little sloppy and not write units all the time now. So in this case then, it looks like it's -1 minus -2, or -3. And then you have 2 minus 2, or 0 in the y direction. So this looks like it is just -3 x hat, if I want to write it using x hat instead. So that is the direction, and again, it points to the left. Does that make sense? This is supposed to point to Q1 from Q2. Indeed, it should point to the left. All right, I guess I'll write the y hat too, plus 0 y hat. The magnitude of this vector, the square root of the dot product, so it's the square root of -3 squared plus 0 squared, which is square root of 9, which is 3. Not too surprising. And then the unit vector is 1 over the magnitude times the original vector. So it looks like it's 1 over 3. And the original vector was -3, 0. Or this just becomes -1, 0. Or, again, -x hat. Which, again, makes sense. We know that it should point either to the left or to the right. And this position vector is entirely horizontal, pointing to the left from Q2 to Q1. Notice how I also just very systematically went through this as well. Right? Given the position vectors, I could get the relative position. I then got the magnitude. I then computed the unit vector. Then we put it all together and see if our formula works. Then F, Q1, Q2, looks like it's going to be then K, -E, -2E, all over the magnitude squared, so all over 3 squared, times R hat, which we said was -x hat. Two of those negatives cancel, and it looks like I get -k, well, there's a 2, e squared, all over 3 squared, which is 9, multiplied by x hat. Two of the negatives go away, and there's one negative still left over. And the e's become e squared, but the 2 is not squared. But the 3 on the bottom is. And so this seems like it's in the x direction. And because of this negative sign, points left. That seems correct. Can I do it for Q2 on Q1? Sorry, on Q2 from Q1. Well, we just got to be careful of what we did. This formula was for on Q1 from Q2. We evaluated this where R was R1 minus R2 when we did on Q1 from Q2. So if we're going to do Q2 from on Q2 from Q1, we just got to flip everything. This will stay the same, but then this will have to become R2 minus R1 instead. Or if you want to think, well, I'll do that in a bit. So then, again, R then in this case is going to be R2 minus R1, which R2 we said was do columns this time. 2, 2, and R1 was -1, 2. So in that case, when I do the subtraction, it looks like I get 3, 0, or plus 3 x hat. Again, shouldn't be too surprising. then the magnitude looks like it's, again, just 3. And the unit vector looks like it's going to be plus x hat in that case. So then when I put it all together, Q2 from Q1, I have k, negative e, negative 2e, 3 squared on the bottom. And then it looks like I have plus x hat in this case. The negatives cancel. It looks like I have 2k e squared all over 9 times x hat. It points, in the x direction, and overall it's positive, which means it points to the right, which is what you would expect, going back up to the problem. If they both are negative, I expect then the force on Q2 from Q1 to point that way, just like the force on Q1 from Q2 is pointing this way. So indeed, this is a general formula that works, as long as you kind of follow the steps. If you're doing on Q1 from Q2, then this vector is RQ1 first, Q2 second. I might even try to do it without numbers in case the numbers are throwing you off, right? If the force on A from B is going to be K, Q sub A, Q sub B, this position vector squared times R hat, where the position vector is going to be RA minus RB. So, again, I would think of it as on A from B. If that's what you're doing, then it's RA minus RB when you do the position vector. And we can think geometrically first. Does this make sense that it should work even when things are not, say, nice horizontal lines? So let's have x hat and y hat again. And suppose I have Q1 here and Q2 here. Well, the line connecting the two is going to be something like that. Then I have, sorry, I just touched the mic. Then there should be this outline. So that's R1. The position vector 2Q1, position vector 2Q2. And so then if I wanted to do the force on Q1 from Q2, then the R vector, we said was going to be RQ1 minus RQ2, which is going to point to Q1 from Q2. Is going to point then just by the definition of vectors, how you add and subtract vectors. It's going to be pointing in that direction. And indeed, it falls along the line as we expect, that dotted line. So this formula will even work when things are not nice horizontal lines. Let me do one more example, and then that'll be it. Let's imagine an equilateral triangle. So, OK equilateral triangle. There's a charge on, maybe we'll do A, B, and C this time. There are charges Q, A, QB, QC on the edges, and the side of each side of the triangle has a length of well, let's just leave it as R. And then suppose we're told that QA has a charge of negative E, QB is positive E, QC is also positive E. And the question is, what is the force on Q sub A net? What's the net force on that top charge? And I would like to write it as a vector. with components. And we can think first, I always like to think, by the symmetry of the situation, because again, all these are R. By the symmetry of the situation, I know that QA is going to be pulled in this direction. So that's on A from B. And I know it's also going to be pulled in this direction. That's going to be on A from C. And again, since the two charges are the same in the bottom and the lower corners, seems like I might expect by the symmetry of the situation that the net force is going to be perhaps pointing straight down. Let's justify that. Let's compute that. Okay, so I'll do one of them, and I think you'll be able to reason out the other. Again, you could use symmetry as an argument. So, which one should we do? How about we'll do force on A from B. So, by our formula, I need to know now the position vectors for charge A and charge B before I can continue. So if I go back, I should have actually copied and pasted this. Let me actually do that so that we can look at it. In order for me to use this, it essentially hinges on me being able to evaluate R, because I need the magnitude squared, and then I need R hat. So I need to be able to figure out what this R is, which if I want on A from B, it's RA minus RB. So I need these position vectors, which means I need to specify some coordinate system, because these are measured from the origin of that coordinate system. Now, of course, you can use whatever coordinate system you want. So, given the freedom, the problem doesn't demand a particular coordinate system. Put your coordinate system down such that your life is easier. Such that it simplifies things. Simplifies things. Now, how could I make my life easier? I could put the axes so that they're kind of rotated along one of the directions of the triangle. That would be a way of doing this. I could also put the charge of interest at the origin. So, in this case, copy this here. And what I'm going to do, let's see, what of this can I erase? It's hard to erase those. The wrong color. Does it really matter? Well, too late. In this case, why not put the origin, since we're focusing on Q sub A, why not put the origin on Q sub A? So let me see, what color? I'll use green. That's my coordinate system. I'm going to put my coordinate system such that the origin is right there. That's going to make my life easier. Why? Because then the position vectors, in that case, this is the position vector R sub B. This is the position vector pointing from the origin, right, to the charge. Just happens that one of the charges is also at the origin. And then R sub A is a 0 because it's at the origin. So then if I want to do the force on A from B, then I need the vector RA minus RB. Now, my life gets easier because R sub A is at the origin. So the first vector is 0. So this is just 0 minus R sub B. But now I need to figure out the coordinates for r sub b. So if we go back to the triangle, the equilateral triangle, I can try to see, how can I figure this out? Here's the origin, and I want to essentially figure out this vector here, which is conveniently along the length of one side of the triangle. Particularly, I notice if I do this, if I cut the triangle in half, I have a right triangle. Essentially, most of our physics toolboxes look for triangles. So let me just redraw that triangle here. I know this length is r. This length is, I guess, r over 2, because it's cutting the equilateral triangle in half. And then I don't necessarily know the height of this equilateral triangle unless I figure it out. And I want to find the coordinates, the xy coordinate for this point, which means I need to find, how much I go down in the y direction and then how much I go right in the x direction. By the problem, seems like the x is already figured out. That's nice. So I just need to figure this out. I suppose maybe you don't even know this. I'm going to take this away. And suppose you didn't even know that about the symmetry of the situation. Then what else do you know? You know the side has length r. You also know what this angle has to be. If it's an equilateral triangle, then each angle in the original triangle is 60 degrees. So this theta is then 30 degrees, or pi over 6 radians. And then we SOHCAHTOA our way to paradise. So the swoosh is touching the vertical side. So then the y side here looks like it's going to be r times cosine of theta. And I'm going to throw in that negative sign because I know it's going down. So then it looks like it's negative r cosine of 30 degrees, root 3 over 2. And then x is positive r times sine, which then looks like it's r times a half, or r over 2, like we had before. So then Q2 is at coordinate r over 2 in the x direction, negative root 3 over 2r in the y direction. All right, it goes to the right and it goes down. All right, so then that is R2. I move this over. Is that R2? Is that? Why do we need this again? Because we need R. Oh, sorry, I've switched from letters to numbers. This is QB, RB. Yes, okay, good. So then originally we were trying to find R, which was RA minus RB, which is 0, or I'll write it, and I'll go back to columns again, right? It was 0 in the x, 0 in the y, because it's at the origin, minus, and then we just figured out that this is r over 2, root 3r over 2. Notice the minus, and this minus is because it's the difference of two vectors. It has nothing to do with the coordinate system. This minus has to do with the coordinate system. So then it looks like that is 0 minus r over 2, so negative r over 2, and 0 minus negative root 3 over r over 2, so then that's positive root 3r over 2. This looks like it points left and up. It's negative x and up positive y. That makes sense because this is supposed to point to Q sub A from Q sub B. So I like it so far. That's the position vector. The magnitude is then, again, root of the dot product, square root of negative r over 2 squared plus root 3r over 2 squared. And that looks like it is root r squared over 4 plus 3r squared over 4, or just square root of r squared, or r. Again, not too surprising. You probably didn't need to do the dot product to do that, because we originally drew it so that they were a distance r away, because they were at the edges of the equilateral triangle. But it's always nice when the math corroborates. So then r hat is 1 over r times, I'll write as a column again, the original vector, negative r over 2, plus root 3r over 2. It looks like the r's cancel, and it looks like a column vector that's negative 1/2 and positive root 3 over 2. Notice now there's a component for each, right? So it looks like it's 1/2 x hat, sorry, negative 1/2 x hat plus root 3 over 2 y hat. Points left and up. And this is a unit vector, right? You could test it. You can test that. R hat dot r hat on the square root does indeed equal 1. And then we put it all together. Force on A from B is K Q sub A, which I said was what? Negative E. Negative E. Q sub B, positive E. All over the magnitude of the vector, which was r. So then we got to square it. Then r hat was negative 1/2, comma, root 3 over 2. So how can we simplify this? I could yank out a 1/2 from the vector. Well, as is, again, this is, maybe first I'll just put the negative sign inside. So I have k e squared over r squared. Then that negative flew in, so it's now plus 1/2, comma, negative root 3 over 2. This, again, is the magnitude. That is the direction. Magnitude looks like it's kqq over r squared. The direction looks like it points to the right and down. Is that what we expect? Indeed. We expected that it should point to the right and down. Now I write it like this because the direction here is a unit vector the way I've drawn it, though you might want to simplify this. Like for example, there's a 1/2 in both terms, so I could yank out that 1/2. So then it's k e squared over 2 r squared, and then what's left over, it looks like it's 1, comma, negative root 3. Which again is giving you the same direction, of course, but 1, comma, negative root 3 is not a unit vector. Though of course this is the same thing, right? I just yanked out that 1/2. Or if I want to write it all together, right, that's k e squared over 2 r squared in the x direction, negative k e squared root 3 over 2 r squared in the y direction. Now, I'll let you try the force on A from C, and you should find that you get k e squared over r squared, and instead get negative 1/2, comma, negative root 3 over 2. Points left and down, which if we scroll up is what we expected. It should point left and down because they are attracted to one another. And so then, if I take this and I guess this, I'm going to go around this, essentially that and that, which those are connected, and add them together, right? What is the net force? F on A, and that's F A from B plus F A from C. And then I just add the components. Looks like component-wise, I have, well, they both have a k e squared over r squared out front. So I can write k e squared over r squared out front. And it looks like I have a plus 1/2 minus 1/2 in the x direction, and a negative root 3 over 2, and a negative root 3 over 2 in the y direction. Again, there's a plus 1/2, and then you're adding to it a negative 1/2. That's where this is. You have a negative root 3 over 2. You also have a negative root 3 over 2. So then that's where that is. So then what's left over? K e squared over r squared. Then the x direction goes away, and it looks like you have 2 times that, or just negative root 3. I need a little bit more room. Move this over. Right, there's no x component, so it looks like it's k e squared over r squared, negative root 3, I'll bring that out, times y hat. It points vertically downward, as we expected. Now you can try doing this again for the other charges on the other parts of the triangle. You might use a different coordinate system, right? You might put that charge at the origin if you wanted to. That's perfectly okay. Because again, we're not talking about positions here, we're talking about forces. So we don't necessarily need the origin in a specific place. All right, so really only positions where you measure relative to the origin. All right, so there you go. Systematically, how we do this. If this were 3D, nothing would really change other than there'd be a third coordinate. So again, if I want the force on A from B, then these are just numbers in the numerator. But if it's on A from B, I have to do RA minus RB. I then take the magnitude of this thing. That gets me that after I square it. Then once I have the magnitude and this, and if I have the magnitude and the original vector, I can then compute the unit vector. So it seems like the steps, steps of that, step 1, compute R, which might itself require a coordinate system, right? That might require you to write down a coordinate system. Once you compute R, then you compute the magnitude. Then you compute the unit vector. And then you put it all together. All right, let's see if now we can do this on our own. Again, I've tried to make it essentially algorithmic, where if as long as you're careful with the math, this will always get you the right answer, which can be helpful. But again, notice how even though we have this kind of algorithmic approach, I'm still thinking along the way of what I expect the force vector, where I expect the force vectors to point, for example. And then you're seeing more examples of how I'm utilizing symmetry, where, on an exam, if you can argue via symmetry, you are absolutely allowed to do that. You can skip the math if you can argue via symmetry, because I think that skill is powerful. So if you were able to see this and say, okay, by symmetry, the arrow should add up to be purely vertical, right? That would be a plausible argument in my book. Now in this case, I wanted the actual vector, right? So you still had to do some math, but always be on the lookout for symmetry. All right, very good.